Alright, so the first problem we're going to be trying is a goodness of fit test, and this is the question. Many people know that mathematic constant pi is approximately 3.14, but that's not exact. To be more precise, here are 20 decimal places, a large number. Still not exact though. In fact, the actual value is rational, a decimal that goes forever without any repeats. But you'll notice that there are no zeros or sevens in the stated one before. Does this pattern persist, or do they show up equally? The table on 643 of your books, ladies and gentlemen, will let you know. Now we're going to test the hypothesis using that table, using the digits 0 through 9, to see if they're uniformly distributed in the decimal approximation of pi. Great. So, like I said before, this is going to be a goodness of fit test, which means that there's only one column of data that we're working with, which right now is the counts for the digits of pi. Now, like I said before, if you could all just go to page 643 of your books, you'll be able to look at what the observed values are. However, right now what we want to focus on is what our hypotheses are. And it's a goodness of fit test, so let me just write this here. And now what we want to do is get two different hypotheses. One, which is what we're the null hypothesis, which is what we're pretty sure it is, and then there's the alternate hypothesis, which is what we're testing for. And I'm going to write them now. So the null is always in terms of h sub O, and the alternative is h sub A. Alright, in context of this problem, it wants to know if the digits are uniformly distributed in the representation of pi or if they aren't. So our h sub O would be just that they are, because that's the first thing that I stated, and it would make sense that, equal would be what we would expect it to be. So we're going to write that. The digit, they're uniformly distributed. All right. Are uniformly and then ultimately our null is just going to be that they aren't. So as you can see here, that they're uniformly distributed or that they aren't. Now, in a proper test, if you were taking the actual AP exam, you would probably want to rewrite this exact sentence just opposite instead of just that they aren't, but for time reasons, I'm going to condense it. So now that we have what our null and our alternative hypotheses are going to be, we're going to write out the assumptions and the conditions that will go along with this. Each test that we do in statistics has these assumptions and conditions, and they go specifically with what we're doing. Now, for the goodness of fit chi-square tests, the assumptions and conditions are as follows. That they must be counts, that it must be randomized, that it must be less than 10% of the population, and that the counts must be greater than 5. It's a less than symbol. Greater than 5. For this, what we have here is all of the conditions and assumptions, and I just read over the book, and what it says is that it is a count, obviously, because we have the numbers as our data. Rather than qualitative data, this is quantitative data, so we have that, and then you would just write that in a sentence, that the data are counts. Randomization, and technically it is stated that all the digits are chosen at random because this is an irrational number and there is no patterns. So we have that. And then less than 10%. Now, the amazing thing about pi is that it goes on forever, so no matter what, the digits that we're given will be less than 10%. Finally, what we have is the expected counts must be greater than 5. So, I'm sure you're all wondering, how would you find the expected counts if all we have in the book, that I'm sure you're open to right now on page 643, is all different numbers that wouldn't really make sense for expected when they're observed. So what you're going to do is you're going to take all of this, and you can see that there are 10 digits. So you have 10, and you know that they just said that it's the first million numbers. So you want to do 1 million divided by 10, because all of them, according to the null hypothesis, which I wrote earlier, are equal. So it would be 100,000. And as you hopefully know, 100,000 is greater than 5. So we have that. Now, as you can see, there are checks everywhere where there should be. So we may continue with our goodness of fit chi-square test. What I have here is the next step in the process. And what it is this huge table. Now, we can condense it later on, but for now, since you're all learning, I'm not going to. And what it is I have all the digits of what we're testing, so all the digits of pi, and then I have all the observed, all the expected, and then we're going to go through. I didn't write down all the observed because you're looking at the page right now in your books on page 643, and the expected is just always 100,000. So I'm going to go through the first one or two with you right now. So observed for 0 is 99,959, and the expected is 100,000. Now, the first step is just observed minus expected. So, really easy. Just that. And then you want to square it. Yeah, there we go. And then you would just take this, you would square it, and then you would put it over the expected. So if we were to do this right now, you would end up with a pretty big number and a whole lot of calculations for all of these. So I'm sure you're all wondering how we can condense this whole entire chart into one really simple number. Because after you do each and every one of these rows, you're going to want to add this columns all up. And that's what makes chi-squared. Because the actual equation for chi-squared is as follows. The sum of observed minus expected over expected. And observed minus expected is squared. So what this means is that this entire chart that I had before is what it was saying, leading up to the observed minus expected squared over expected. However, this is the part that I left out, which is the sum of, which means you add up this entire column, all of the data that's in it. And as I was saying before, it's a lot, and I'm sure you're all wondering how we can condense it. And quite simply, we can condense it using this calculator. So here we have our calculator right here. And now, in order to condense it all, we're going to use this calculator, and we're going to start off by entering in our data that we had before, which is the observed and the expected. And what I want you all to do is go to Stat, and then to Edit. And you're going to see it. It's going to be the first one. Just edit. And for L1, it's going to be all the observed values. And then for L2, it's going to be all of the expected values that we had before. And as I said before, all the expected values are 100,000 because it's 1 million divided by 10. And then the observed are on page 243 of your textbook. So now that all of your data is entered in, what we want to do is the same thing that we were going to do before, which is find chi-squared. So what I want you all to do is to go again to Stat, and then go over to Tests, because that's what we're going to do now. So we're going to go to chi-square test, goodness of fit, because that's what I keep writing, because that's what this is. And then we're going to click it, and it's going to say observed, which is L1, and expected, which is L2. But then it's going to ask for DF. DF stands for degrees of freedom. What you want to do is you want to take all of your observed or expected, because they should be the same amount, which is 10, and then your degrees of freedom is going to be 10 in this situation minus 1, which is 9 in this situation. So your degrees of freedom is going to be 9, and then you're just going to press calculate. And what you end up with is a chi-square of 5.50908, which leads me to my next part, which is explaining what that chi-square value means. Here, we have what this matches up to. We're going to say that right here is what this lovely chi-squared is, which is 5.50908. And what we care about is what's to the right of it, right here. And this is our p-value. And right now, what our p-value is, which it also tells you in your calculator, is 0.7878669. Which, in my vast experience, I can tell you, this is a very big p-value. Now, what this p-value tells you is pretty much everything you need to know. Because for this equation, I didn't mention it before, but what we have here is an alpha, which is 0.05. And anything above 0.05 means that the null is true. And anything below 0.05 means that the null is false and on a hill. So, as you can see over here, this huge p-value of 0.78 is way larger than 0.05, which means that our null, which we discussed in the very beginning, which is that all of these numbers have equal frequencies, is true. So doing all of this test has thus proven that because the conditions were true and that it matched up with what we wanted for a chi-square goodness of fit test, that it is true. Thank you. So what I want you all guys to do is you're going to go to page 648 of your textbook and you're going to look at number 41. And number 41 is all about pregnancies. And what it is a test of independence to see whether or not it is independent that live births and fetal losses are independent of age or not. So your null hypothesis, which is the one that we're trying to, in this situation, prove false, is going to be that they are independent of each other. So what you'd want to write is pregnancy, death, and age are independent. Are independent. And for time purposes, I'm just going to write that they aren't. But for like when you're writing this on test or on homework, you're going to want to write it out more, but just that they aren't. Next up, we're going to check the conditions and the assumptions. And for this, always write, as you can see, there are numbers and therefore they are counts. Next up is randomization. And what we have here is it says, written down right here, that, well, it doesn't specify that it is random. We're going to say that it is representative of the population, so that's checked. Next up we have, is it less than 10%? Now, our total number of mothers is roughly 400. However, when you multiply 400 by 10, it's 4,000. So, we're going to say that 4,000, it's probably very likely that pregnancies exceed 4,000, given, the wide range of ages and how, people get pregnant a lot. So, it is checked that 400 would be less than 10%. And then the next would be expected counts greater than 5. Now, the way that we're going to check that is a little bit different than before. Before, in the last problem, we could just divide. However, in this situation, we're going to have to use our calculator. So, what I want you all to do is get out your calculator and go to second matrix, and then edit the first one. And you want it to be a 4 by 2 table. And then you're just going to type in all of those numbers. Give me a second to do that. 41, 88, 21. Alright, and then once you do that, these are your observed. You're going to go to stat, test, just chi-squared, which is C. It's right above goodness of fit. And your observed, which is A. Your expected is B, which may seem strange because we didn't type anything into B yet. However, it's going to type it all in for us, so it will work out perfectly. And then calculate. It's going to give us a bunch of things that we don't care about yet because we don't even know if it's right if the conditions haven't even been met. So you're going to go back to the matrices, look at B, and 49, 12, 193, all of these are higher than 5. This is checked. So, move on. Because it's a chi-square test, we're still sticking with this equation. And you write out the entire chart, and you could write on a test, just for this equation, just like 3 and then like a dot 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 equals chi-squared. But for us, for time purposes, we're just going to go over to test again, the chi-squared test, calculate, and it gives us our chi-squared value, which is 5.89. Now, if we draw this out, yeah, that's nicer. We have our 5.89 here, and we're going to shade this in, and this is our p-value, and our p-value given to us in the calculator is 0.11733. Now, I forgot to mention before that we still care about our degrees of freedom. We still want to write them down, even though the calculator gives it to us. So what I want you guys to do is I want you to take the number of data in columns, -1, and the number in rows, -1, and multiply them. So in this situation, our rows are 4, so 4 minus 1, and our columns are 2, so 2 minus 1, and then you end up with 3 times 1, 3 times 1 is 3, and you end up with 3 degrees of freedom. And you're going to want to write that down. So, now that we have our degrees of freedom, we can look back to our p-value, and we can see that it is 0.11733. And for those of you who remember before, our alpha is 0.05. And like I said before, anything greater than 0.05 means that the null is true, and anything less than 0.05 means that the null is false. So for us right now, it is greater than 0.05, which would mean, therefore, that they are independent of each other, meaning that it does not affect the live birth rate and the death rate of babies your age.